Analysis of compound. Like HI, for example. This is draw the Lewis diagram. This is a homework. I forgot to post the homework for chapter 13, but I'm going to do that soon. HI. HI is a pretty simple Lewis structure. It looks like this. All diatomic molecules are linear. Because you got two atoms, you're only going to have a straight line type structure. But how would we name it? We have two different names for HI. One name is in gaseous phase, HI gas. The other name is HI aqueous. What do we call HI gas? Pure hydrogen iodide. And then what's HI aqueous? Hydroiodic acid. What are some of the chemical properties? Yeah, HI is a strong acid. It's near the top of the chart, for sure. HI is a strong acid. How about iodide? Is iodide a very strong base? Iodide is an exceptionally weak base. It's like chloride. You aren't going to neutralize anything with that. And so HI is a strong acid. That's pretty much it. Is that it for chemical properties? What other chemical properties do we look for? Redox. We look for redox. We look at the redox properties. What can you tell me about the redox properties of HI? Well, if we're looking at the formal charges, does anything look electron rich or electron poor to you based on formal charge? H plus we know. Let me just tell you. H plus is a oxidizer. But what about iodide? Iodide is a decent reducer, unlike chloride. Chloride's an awful reducer. Chloride's way up here. But iodide is pretty decent. It's a big atom, so it's not terribly hard to ionize it. Ionization energy. So iodide can be oxidized. You know, metals are electron rich, so iodide is similar. And so it's both an oxidizer and a reducer, although it won't react with itself. You know, H plus is not strong enough to oxidize iodide. H plus is not strong enough to oxidize iodide. We need something stronger. We need something at least as strong as what? Oxygen, iron 3, silver ions, etc. Those will oxidize it. And then we have one more chemical property that we look at, which is what? Metathesis. H plus, there's certain ions that it likes. I minus, what ions does I minus like? Give you a hint. Chlorides, bromides, iodides. Like what ions? Chlorides, bromides, iodides, like positive ions, yeah. All of them, or some of them? Just only 3 of them. The first row, the first column. If forced, it'll be there, but there's some 30 ions that it in particular likes a lot. Iodides like. Yeah, silver, lead 2, and mercury 1. You know, if iodide encounters silver, we'll get a precipitated silver iodide, and again, lead-2 precipitates lead-2 iodide, and mercury-1 iodide. And so those are some of the properties of that. Well, water, we know. You know, what are the chemical properties of water? Probably pretty much already know that. Does water participate in metathesis? No. How about acid base? Is water a strong acid? No. Is water a strong base? No. How about redox? Is water a strong oxidizer? No. Is water a strong reducer? No. And so water is pretty stable, you know, which is a good thing. You know, blue keeps Earth blue, I guess. Blue planet. Anyway, going on to NCl3. What about NCl3? NCl3, now this is where we can use Lewis structures to help us understand it, because this kind of looks like NH3. You know, NH3, we've seen that before. We know one or some of the properties of NH3. Can you remind me of what properties of for NH3? I know it was a while ago, but what are some of the properties of NH3? Yeah, so you're saying NH3 is an acid. Is that the first property that comes to mind? When I think of NH3, let me tell you the first property that comes to mind. Weak base. You know? When I think of NH3, I think, oh, that's a weak base. Because I've looked at this chart so much. Here is NH3, weak base. It's also a weak acid, but it's an exceptionally weak acid. Most people don't think of NH3 as an acid. You need a very powerful base to react with NH3, like oxides, hydrides, methides. Very powerful base. You know, have you ever heard of this professor at USC, George Olah? He won the Nobel Prize in Chemistry not so long ago. His work is with superacids and superbases. Superacids and superbases can do some unusual reactions to make new things. Like, one of the things is making gasoline, synthetic gasoline, from simpler hydrocarbons. Gasolines are complex mixtures of hydrocarbons. You know. Anything else? Oh, that's acid base. Metathesis, it reacts indirectly. What about redox? Redox, ammonia, we'd say is electron rich. Ammonia, the nitrogen in ammonia is electron rich. So when we go to NCl3, let's go ahead and do the Lewis structure. NCl3 looks a lot like ammonia, but there's some major differences. One, are there any formal charges? Ammonia has no formal charges. How about NCl3? NCl3? No. But one of the things about ammonia that makes it, ammonia has a proton acceptor. You know, proton can come over here attached to this, make it NH4 plus. A proton can do the same thing, come over here and attach to this. So this kind of looks like a base like this, you know, it's because of the nitrogen. The nitrogen makes this basic. And so would you expect this one to be a weak base like this? Now, we do. We expect a lot. Do you remember the amino acid we did the other day? The amino acid, glycine? If you look at the structure of that, the structure of the amine part of the amino acid is very similar to ammonia. And that amine part is basic. And so this, this could go by different names. We could call this, what are the names we could call this? NCl3. You could call it, we can call it nitrogen trichloride is one name. Another name for this is trichloroamine. But that's not the appropriate name for this, because this doesn't behave like a base like ammonia does. And the reason is because of dramatically different electron distribution. If you take a look at the molecule on the right, what do you notice? Can you see the numbers when you count the electrons? Can you see a difference? When we look at formal charge, there's no difference. Formal charges look the same. But when you look at the oxidation state, you'll see a dramatic difference. What was the oxidation state of nitrogen here? -3. What do you think the oxidation state on this nitrogen is here? No. +3. The oxidation state is +3. That's a huge difference. One's -3, the other +3. Do you think they're going to behave similarly? No, they aren't. In fact, they're totally different in terms of behavior. This is a pretty good reducing agent. This is not. If anything, this would be more of an oxidizer than a reducer. Also, base properties. This one's basic. A base, this is not. And so, the structural aspects of this can tell us some about the chemical properties. Especially if something that's not on the charts. We don't see NCl3 on the charts.
So is NCl3 more acidic?
Well, it's a bit trickier than that. As far as its properties. It's just much less basic. Put it that way. It can turn acidic depending on what's bonded. Since we have chlorines bonded here, it's not. If I had a hydrogen thrown up there, hydrogen and 2 chlorines, then it would be a lot more acidic than ammonia is. But that's figuring things out. Once we see more of the pattern and get it. All right, so there's other small molecules and ions, like hypobromite, ammonium, perchlorate. Perchlorate's more tricky. We also might have ring structures that are potentially possible. Those are Lewis structures. But we also want to deal with shapes too. So let's take a look at this molecule here. Number 24. This one. See, well, normally I wouldn't write it like that for you. This is giving too much of a clue. And this is called the condensed structural formula. Condensed structural formula makes it a lot easier. Condensed structural formula is a lot more informative. So for example, if you had to draw the Lewis structure for acetic acid, and I gave you the regular molecular formula for acetic acid, HC2H3O2, versus the condensed structural formula for acetic acid. The condensed structural formula would be CH3COOH. So depending on which of these I give you, then the proportion of wrong answers I get on the test are quite a bit different. Like if this one, I get a lot more wrong answers. one gives you a little bit more information. And so this is maybe too informative here, but it's all right. We'll just go with this. So what are we going to do with that formula? This is what I want you to do. For each molecule, write the Lewis diagram, then describe A, the electron pair geometry, and B, the molecular geometry predicted by the valence shell electron pair repulsion theory. Also sketch the wedge and dash diagram for each molecule or ion in question. And so first off, why don't you sketch the wedge and dash diagram for this? Can you tell me the name of this? It's all right. Just draw the wedge and dash diagram for this. See, first you got to draw the Lewis structure. So draw the Lewis structure. If you want to get the Lewis structure checked out, I'll check it out. If you need help, let me know. If you want a hint, I'll give you a hint. The hint is, look at glycine. Did anybody write down the structure of glycine from Thursday? This morning I was a bit surprised nobody wrote it down.